Hello everyone. If you're actually watching this part of the video first, I suggest you go back and watch the first part, which deals with the 1D and 2D objects. However, if you're already familiar with how to derive them, then I suggest you keep watching them and see how it's done for 3D objects. So yes, we'll be continuing with the moment of inertias for 3D objects. First one is that of a hollow cylinder. So the hollow cylinder is actually remarkably similar to a hollow ring. Or ring, we don't have a hollow ring, except that it is actually extended in space. Let me try if I can actually accurately make a cylinder. So we're going to extend this like this, and we're going to add another oval here to signify the fact that this is a cylinder. Okay, I think that's I think that's fit there. Oh yeah, it actually fits, so that's pretty good. So what you're trying to do here is we're trying to find the moment of inertia about a center of mass, or the axis passing through a center of mass. So suppose the center of mass is somewhere over here. In two dimensions, we generally consider an axis to be a single point, but here in three dimensions we consider it to be a line. All right. Again, this is a straight line. Wait, why don't I actually use this? Oh, I never actually thought of it. Oh wow. So yeah, we can just use this to denote the axis. So each point on the hollow cylinder is actually exactly r naught distance away from the center of the axis, or the axis basically. Alright. So all we need to do is we need to do the integral over all of these mass elements. So this case is actually pretty simple to do. So as you'll see, this is exactly similar to what we did in the case of a ring. So you're going to write I is equal to integral dm r square from 0 to m. We can take r square out because this is basically r naught for each of these. So we can write r naught square into m, that is the total mass of the cylinder. Alright, so that's done for a hollow cylinder. Now we'll move on to a solid cylinder. And again, this case is extremely similar to that of the disk because it's basically the same thing. We're just extending the disk to a three-dimensional case. So we are going to draw another cylinder over here, or I could copy paste this cylinder. Why am I drawing another one? So I'm going to select this, alright, and I'm going to copy and I'm going to paste it over here. Okay, so that's that. And I could also fill it with the color to indicate the fact that this is actually solid. So we're going to fill it over here. Yeah, I think that makes sense. I realize it looks a bit different, I guess. Yeah, but yeah, you get the idea. It's a solid cylinder. So here we are going to define the actual. Let me change back to that. We're actually going to define density with rho, that is actually volume density, and we're going to write m by v dv. Alright, so we'll allow this thing to have a length or a height. We usually say the volume of the cylinder is pi r square h, or we can say L also, it really doesn't matter, I guess. Alright, so the volume is defined as pi r square L. Right? Now this is not the total volume that we're defining here. Just to make it clear, this is V naught. V naught is equal to pi r naught square L, and V is simply the volume of any cylinder of r length r, because here we're using the same idea that we did in the sphere in the case of the disk, my bad. So what you're going to do is you're going to consider another cylinder over here that is extending like this as well. So it's like this, and so it has the same length L, but it has a radius r, and it has a thickness dr. It is at a, so that's what we're aiming to do over here. So dv by dr is actually equal to 2 pi r l. Again, I'm applying the power rule here. I also did that in the previous case for disk. And so dv is simply equal to 2 pi r l dr. Then now we're going to write I is equal to dm r square. So this is equal to, I'm going to write this as, oh yeah, but this is not, oh god. I'm so sorry if you were confused there. You probably were. This is actually dm. I'm so sorry. We are writing rho as m by v naught. Okay, I'm so sorry. So 0 to m, and we're going to write this as rho into dv r square, 0 to l, all the volume, because it's actually still dv. So we're going to take rho out, and we're going to write this as 0 to r naught dv. So this is dv is actually equal to 2 pi r l dl. So we're going to write this as 2 pi r cube. Well, let me just write l here so it's clear. R cube dr. So dr here. There's no dr here. What am I doing? There's no dr here. There's a dr here now. So m by v naught into 2 pi l, and we have 0 to r naught r cube dr. So this is equal to m by pi r naught square l 2 pi l r raised to 4 by 4 r naught and 0. Okay, so we're going to cut pi, we're going to cut l, and we're going to write this as 2m by r naught raised to 4 by 4 r naught square. We'll cut the first one over there, we'll cut this entirely, we'll write this as 1 and we'll write this as 2. So as you'll see, the result is identical to that of the case with disk, and they're actually really similar when you actually look at them. Okay, so this is the moment of inertia of a solid cylinder about its axis. This might have confused a few of you over there. I'm really sorry for that. We're actually writing rho as m by v naught. Okay, so that concludes our case of a cylinder. Now we are going to move on to spheres. So this, I believe, is the one that I found most difficult to do or a little to understand. So let's see how it goes. I am actually also quite confused as to how I'm going to draw a sphere in 3 dimensions. I mean, as to how I'm going to draw a sphere. Let's see. So the first case that we're going to do is that of a hollow sphere. Alright, so okay, so we're going to evaluate its moment of inertia about its center of mass. So here we have its radius r naught, and what we are going to do is we're going to consider elements dm about its a perimeter, small perimeter like this. Okay, so assume that this is a small length like this and this has a mass dm. Okay, so the length of this would actually be equal to, so we are going to have this over here, and so we are going to have a theta over here, and so the perimeter of this would simply be equal to 2 pi r naught, okay, but sine theta is going to be there. Alright, because this length over here is going to be r sine theta. So when it is over here, theta is going to be 90, and it's simply going to be the 2 pi r, the whole thing over here. But when it's actually up here, it's not going to be 2 pi r, the whole thing. So we are actually going to take 2 pi r naught sine theta to get the perimeter of this. I don't even know what to call this. Is this like, yes, this strip over here. To get the perimeter of the strip over here. And then what we're going to do is we are also going to get the thickness over here. Okay. Now the thickness is actually simply r naught into the d theta. Okay, that is because what I want you to think of it as is like the arc of a circle. So this arc is actually is the radius over here. We're going to extend the radius over here, and there's going to be an infinitesimal increase in angle theta, and that's going to be equal to d theta. So that's the thickness of this strip. So what's this small area, right? This small area is simply multiplying these two again. You can think of it as a rectangle over here. The strip can be thought of as a rectangle. Its length or its perimeter is equal to 2 pi r naught sine theta, and its breadth is equal to r naught d theta. So we are going to write this as dA is equal to 2 pi r naught sine theta r naught d theta. Okay, this is dA. Okay, so and also we are going to define dm again as here. Since we have dA, and we can take A as we can define the area mass density, and the area is actually equal to 4 pi r naught square, because you're talking about the surface area here of a sphere. So we have m by 4 pi r naught square, okay, into 2 pi r naught sine theta r naught d theta. Okay, so we're going to cut r naught, as this thing is entirely gone. This just gets cut, so we'll be left with 2 here. And so we get a really simple and convenient expression that we can use for integration, that is m sine theta d theta by 2. That's it. Okay, m sine theta d theta by 2. Okay, so now we are going to do the integration. So we have I is equal to integral dm r square. But wait, the distance of this from the axis is actually, so again this is a 3D object, so I'm going to draw the axis over here. This axis is, we want the perpendicular distance of this element dm from the axis, so that's actually going to be r sine theta. It's not, the axis is not this point over here, alright? So it's actually a line that is extending through the center of mass. So that distance is actually going to be equal to the perpendicular distance, that is r sine theta. Okay, so that is I is equal to integral dm r square. So we can write this as m sine theta d theta by 2, and again we're going to have r naught square sine square theta, because we are, that's the distance of each element from the axis. This is again going to be an integral. This is 0 to m. With this integral is actually going to be from 0, starting from 0 when this r is at this point, is going to be from 0 all the way around the circle to 180 degree. So we're going to write this as pi here, pi readings. So we're going to take all the commons out, all the common things out. So we're going to write this as m r naught square by 2, yeah, integral sine cube theta d theta. So there are a lot of ways to evaluate this. Two common ways would be to write the identity, that is sine 3 theta is equal to 3 sine theta minus 4 sine cube theta, right? Then we could isolate sine cube theta and substitute the expression, and then we could evaluate further. That's supposed to be a 3. Or for another way to do it is you can take u, okay, you can take u as cos theta, okay. So du would be equal to sine theta d minus sine theta d theta. Alright, so you can write this thing as, we have m r naught square by 2 out over here. Okay, yeah, we have m r naught square by 2 out here. So 0 to pi, we have this as 1 minus cos square theta, alright, into sine theta, yeah, sine theta d theta. So what does this actually come to? You can write this whole thing as, if you substitute this thing over here, we can write this as m r naught square by 2, and I believe it's a negative sign over here, so you're going to have a negative sign. Okay, we can decide it over here. So we can write this as 1 minus u square du. Okay, so when we integrate this, we can write this as, now this will simply be from 0 to, well, u. Okay, so a minus m r naught square by 2, and so we have u minus u cube by 3. Okay, and then we'll substitute what u is here, so we can write this as minus m r naught square by 2 cos theta minus cos cube theta by 3. This is the same expression that you would get if you use this technique here. Okay, and the limits here are pi and 0. Alright, so when you put the limits in there, minus m r naught square by 2, and you'll have minus 1, minus 1, minus 1 by 3, minus 1 by 3. Okay, so you'll write this as minus m r naught square by 2 into minus 2 plus 2 by 3. So that's the same thing as minus m r naught square by 2 into minus 4 by 3 plus 2 cut. So we have 2m r naught square by 3. And this is the moment of inertia of a solid sphere about any of its diameters, or if you can say about its center of mass. Of a hollow sphere, yeah. So once you've done for a hollow sphere, solid sphere simply follows by considering lots of hollow sphere on top of each other to form a solid sphere. So that is what we'll be doing next. So we will go to the next page here. We'll go to the next page and we'll write 8 here, I guess. Yeah. So alright, so again we can consider a solid sphere like this, and we'll put color to indicate the fact that this is in fact a solid sphere. Alright, so then we'll change the color back, and so again you can consider it around about its center of mass or any of its diameters. That will be our axis. Okay, we just shift this a bit away. Okay, so again, really the trick for the solid sphere is to consider it has many shells or hollow spheres on top of each other. So what we're going to do is we're going to define a rho as m by v. Now v in the case of v naught. Yeah. So v naught in the case of the solid sphere is 4 by 3 by r naught cube. Alright. So while this is the total volume, the volume of really any shell of thickness dr can be said to be hold on, yeah, v is equal to 4 by 3 by r cube. That is, it is if it is if it has a radius of r, so it's 4 by 3 pi r cube. So dv in this case, or dv by dr, that is the change, infinitesimal change in volume as you increase the length by dr, if you increase the radius by dr, would be 4 pi r square. And if you take the dv, if you write it as dv, then it will actually be 4 pi r square dr. So yet again, you can visualize this as the volume of a shell of thickness dr. You can consider the black width over here, or the width over here, to be dr, and you can consider its surface area to be 4 pi r square. So the volume of this shell of volume dv is actually equal to 4 pi r square dr. So what we can write it as is, we can write I here as integral di. Okay, so 0 to I. But di in this case is actually equal to 2 by 3 dm r square. Now why is this? This is simply because we are dealing with shells over here, right? These are not point masses. So the moment of inertia of all these shells is actually 2 by 3 mr square that we derived earlier. So this is simply just, we can consider this shell having a mass dm. So the moment of inertia of this shell is actually 2 by 3 dm r square. Alright, and dm is something that we can write from here. Dm would be actually equal to m by v naught, or rho into v naught, into 4 pi r square dr. Okay, so we can write I is equal to 2 by 3, we can take that out, then integral from 0 to r naught m by v naught into 4 pi r square dr. Okay, so 2 by 3 m, we'll substitute the value for v naught, 4 into 3, so we'll cut this 3, 4 by 3 pi r naught cube, that's the volume, into 4 pi, we'll take this also out, into r square dr. That's all that we left with in here. 4 pi, and 2m is what's left. Oh, there's already r square already in here, so this will actually be equal to 4. It's actually 4. So we'll write this as 2m into r raised to 4 dr. So I'm just going to skip applying the limits. You probably know what it is. So 2m by 5 r naught square, and that is the moment of inertia for a solid sphere about any one of its diameters, or you can think of it as about its center of mass. So that was a really long video. It was so long I had to split it into 2 parts, and I guess I did go a bit fast. I am thinking I did, so if I did go, please let me know in the comments. And so I hope you had fun watching me derive these quantities, and if you have any more requests, so please do put them in the comment box, and I will go through them in the next videos. So thank you for watching, and bye.